basically the voltage was negative, so we said it based on the reaction that they gave us, so this reaction wouldn't work. So I'm going to reiterate the signs. If the voltage E is negative, or the cell potential is negative, the redox reaction is not happening. It's not working, okay? It has to be producing a voltage to be working, all right? So from there, we're going to go on and kind of do a practice free response. So a student is cleaning up, wants to dispose of I2 that's produced from a reaction, okay, and they want to convert the I2 to iodide because iodide is easier to get rid of than solid I2, okay? So if they want to convert I2 to iodide, anion, and we're looking at our potentials, going from this is what we need to have happen. The I2 would gain electrons to become iodide ion. That's what they're trying to do. If you need that to work, you need to have a positive voltage. Like, to get the reaction to happen, your voltage has to be positive. So they want the iodine to be reduced, which means whoever they pick to be in the reaction with it needs to be oxidized, okay? And so you go, okay, well, the student has H2O2, hydrogen peroxide, sodium thiosulfate, and Na2S4O6. So then you look down here, and you don't see Na anywhere. Doesn't matter. It's a spectator ion. So like this is this guy, and this is this guy. Okay? All right, and so it says, which solution should they use? Well, if this guy's going to be reduced, the other guy should be oxidized. Okay. What does oxidized mean for these half reactions? Flipping them backwards and flipping their cell potentials. Okay, because these are all reduction. How do I know these are all reduction? Because electrons are reactants. Electrons are going in. They're being gained. Reduction. So how do you do this? Well, if I flip this one, so this is the voltage I'm keeping because I want iodine to be reduced. They say so. So I keep this voltage. I don't touch it. What happens if I flip this backwards? The voltage is what? Negative, correct? And then what happens when you add them together? You get a negative voltage. You think this reaction is going to work? Nope. This guy's out. Now, you need to be careful. Because it's tricky, because that top reaction has both S species in this. Those S anions, they have both of them. So you have to figure out which one is actually the reactant. Well, if this is being reduced and this is being oxidized, it means I have to flip this backwards. 2S2O3, 2 minus, makes S4O6, 2 minus, plus 2 electrons. It's losing electrons. Electrons are coming out. So my two reactants are these guys. So you're going to pick this guy. This guy is a product. Why would you put a product in there? Okay? They want to know who's going to react with the iodine. So it's the sodium thiosulfate that's going to react with the iodine. And then they ask you to calculate the E. Well, 0.54 plus negative, right, because I flipped it backwards, 0.08. And so that's 0.44 volts. Okay. Now it asks you to write out the balanced net ionic reaction. Well, you combine the two half reactions to give us our balanced net ionic. So things on opposite sides cancel, things on the same side get added together. So I have iodine as one reactant. Here it is. My 2 electrons on the left, 2 electrons on the right cancel. I have this guy as another reactant. Products I have, and this guy. So you just combine the two half reactions. The reduction half reaction and the oxidation half reaction. Okay? All right. So we need to talk about free energy, equilibrium, and cell potential. So voltages, equilibrium, and free energy. So you need to remember back in the thermodynamics chapter. When delta G is negative, the reaction releases energy, is spontaneous, is thermodynamically favorable, however you want to call it, and works. The reaction will happen on its own without any input of energy. So delta G is the end-all be-all of whether a reaction will occur. And if it's negative, the reaction happens. Now, I think that the College Board has steered away from using the word spontaneous. Of course, this is me just guessing. Because I think for some reason when kids hear the word spontaneous, you think fast. Spontaneity has nothing to do with kinetics, with the speed of a reaction. Spontaneity is just whether it will or will not happen without you having to put in any energy. So, for example, you take your bike and you go leave it outside. Is it going to rust? Yes, spontaneously. Is it going to rust in 2 seconds? No. But if you leave it there for 3 years, you better believe it's going to rust on its own without any extra help. That is a spontaneous reaction. Now, it's a slow spontaneous reaction, but spontaneity doesn't have anything to do with speed. Spontaneity is, will the reaction occur without any extra input of energy? And if delta G is negative, the reaction releases energy and we can trap it and do work for us, like turn on a battery, turn on a light bulb, supply a voltage, okay? So what does that mean for E? Well, we already know that a positive E means the reaction will occur. If the voltage is positive, it's producing energy, right? A voltage. So look at, this is the equation on your equation sheet. If you plug in a positive E, and F is a constant and N is a number greater than 1, delta G will be negative. Positive E means the reaction happens. Delta G negative also confirms the reaction will happen. It releases energy. And it releases energy, and that's what allows us to produce the voltage. Okay, they all go hand in hand. Whereas if the voltage is negative, if you plug a negative value in for E, guess what the negative and negative do? Make it positive, right? So now delta G is positive. What's a positive delta G? Reaction is not occurring unless you positive add energy. Well, we know that a negative E is a redox reaction that's not happening, which is confirmed by the positive G. You got to put in energy if you want that redox reaction to occur. Okay? And we'll talk about N in a little bit. N is moles of electrons transferred. And so I'm going to do 2 fake half reactions. I'm going to put like 2 electrons here and 3 electrons here. And there's other chemicals. Let's pretend. So this is a reduction half reaction. Electrons go in. This is an oxidation half reaction. Electrons go out. If I were to balance those half reactions, I would need to force the electrons to match. That's the point of redox reactions, right? That's not the point, but that's what you have to do. So how would I get these to match? What would the number be for the electrons? 6, right? You would multiply the top one by 3 and the bottom one by 2, and you'd have 6 moles of electrons. That's what N is. N is the balanced number of moles of electrons from the half reactions. Okay, so N in this case would have been a 6. F is Faraday's constant, 96485 coulombs per mole of electrons, or you can also call it joule per volt mole, and we'll talk more about this later. Okay. They don't give you this anymore. If you don't see the circles, it just means not standard. So let's review what standard is. 25 Celsius, standard conditions, 1 atmosphere. And solutions are now 1 molar. If you are not one of these, you're not under standard conditions, you're under non-standard conditions. All right? For the sake of this class, we very, very rarely, or we actually don't do any calculations with non-standard conditions, but we will talk about it conceptually in a little bit. Okay? So this red one is also on your equation sheet. So the 2 red ones are what's on your equation sheet, which means they're the 2 ones you need to be able to do. And again, it's T, temperature, the negative sign in front. R is the constant. Now let's look at our constants, because we have 3 R constants. And if we're doing free energy, you're going to use the one that has an energy unit in it, aka this one, because it has the joule in it, which is an energy unit. Okay? So that's the R in that equation. See, R. T is temperature in Kelvin. Natural log of equilibrium constant K. And you go, okay, well, what does this mean? Well, let's think about it. So R is a constant, right? Temperature is anything above 0. And so now we're just looking minus natural log of K. And K is products over reactants. So I just substituted K with products over reactants. Let's put fake numbers in here. Take the natural log of 50 over 2 in your calculator, which means lots of products, not a lot of reactants. 50 over 2, natural log. It's a positive number. It comes out to be a positive number. So if K comes out to be a positive number, delta G is negative, which means the reaction works. Think about it. If K is big, it means you have lots of products. If you're making lots of products, your reaction's obviously working because you're getting products. So what happens if I were to flip this? Not a lot of products and heavily reactants. Well, just conceptually in a reaction, if you don't have a lot of products and you have mostly reactants, your reaction is not doing a great job at working. If you have mostly reactants, something's going on. It's not working. It's not favorable. Now, let's look at it mathematically. 2 over 50 is a decimal, right? And then when you take the natural log of it, you get a negative value for the natural log of K. So this ends up being negative right here. Well, the negative and the negative would make delta G positive, meaning the reaction is not occurring when it's heavily reactants. You'd have to add energy to force it to happen. Okay. So we're going to use our reduction potentials right here. It says find delta G and the equilibrium constant for the following reaction. They want to know if it's spontaneous and which way the equilibrium lies. So when we look on here, we have chromium being reduced, and we have manganese being oxidized. Okay, so I'm going to write out the half reactions. Now, you go, well, why are there 3's and 2's and stuff in front? Well, you tell me. Why are there 3's and 2's and stuff in front? Well, because the electrons don't match, right? This is 3 electrons. This is 2. So you multiply this one by 2 to give this 6, 2. This one is 3, 3, 6. And that's what forces the electrons to match. And that's where these coefficients come from. So I need to go to my reduction potential table, though. You can't do that without reduction potentials. So I have chromium being reduced, so I'm going to find that on here. Let's see. Here it is. Chromium being totally reduced. Negative 0.74. Okay? So I'm going to go, and I'm going to keep that guy. Negative 0.74. It's the thing being reduced, so I keep its reduction potential. Now manganese is being oxidized, and my sheet is not an oxidation potential. So I need to find manganese. Here it is, being reduced. But oxidation is the opposite. So instead of writing the voltage as negative 1.18, I'm going to write the voltage as positive 1.18 because I have flipped the equation backwards. And then I will combine them. So 1.18 and negative 0.74 is 0.44. Did I do the wrong voltage on the other slide? So sorry, I was using the number from the following problem. So this is 0.46, that's my bad. I mean, it's close. But the 0.54 plus negative 0.08 is 0.46. I mean, the rest of the answer is still right. I just went too fast when I calculated. Okay. So we're back here. This is 0.44. I did that one right. So that's the E, standard cell potential, voltage. So now we're taking our redox reaction and we're calculating energy. Well, free energy, delta G, free energy. So how do I do that? Well, very easily. There's an equation on your equation sheet. It looks like this. Delta G equals minus N F E. Here it is. Okay, where N is moles of electrons. Well, what are my moles of electrons? It was 6, right? When we combined them, we made them balance out to 6. So N is 6. Okay, so delta G is minus. Now, N is 6. Faraday's constant, you can look up, 96,000. Okay, I want to show you something. 96,485, and I'm going to use this one, joule per volt mole, and the reason I'm going to do that is because E comes out in volts, and you can see the units cancel better, okay? Now, I don't know if you remember this, but delta G and delta H, which we're not working on right now, are, for the sake of this class, I've never seen them not in kilojoules per mole. And you notice that that Faraday's constant is not in kilojoules. It's in joules. So I'm going to cheat and right now change it to kilojoules per volt mole, which just means I'm going to divide by 1,000. There are 1,000 joules in 1 kilojoule. So instead I'm going to write it like this, 96.485 kilojoules per volt mole. Again, I am doing this because delta G is almost always measured in kilojoules per mole, not joules per mole. And so there's N. F. E is the cell potential I just calculated. It was 0.44 volts. Volts cancel. I'm left with kilojoules per mole. Don't forget about the negative out in front. So again, I took this number and I divided by 1,000 to turn it into kilojoules. N is the balanced moles of electrons from the half reaction. So when you go over here, right, we took our two half reactions and combined them. This was originally a 3 and this was originally a 2, and we said, okay, remember during redox reactions you need to force the electrons to match. So I multiplied the top equation by 2 and I multiplied the bottom equation by 3 so that there would be 6 moles of electrons in the top equation and 6 moles of electrons in the bottom equation. And N stands for moles of electrons. It is these guys. So you do get negative 250. It's 2 sig figs because of this guy. Kilojoules. I think it's like negative 253 or 254 or something. Kilojoules per mole. Oh, what do we know about delta G being negative? This much energy is released. And guess what? We trap it and we allow it to produce a voltage for us. It's released and we use it to do work. We're like taking the energy and making it do stuff for us. Run a battery, turn on a light bulb. So again, that negative means the energy is released. It is a spontaneous or thermodynamically favorable process. We already knew that though. Why? Because the voltage was positive. It was producing a voltage. So we knew it worked. The reaction worked. So now, if you know a reaction works, which way should it favor? Which side should it favor if a reaction is working? Products, right? If a reaction's working, you're making products. If a reaction's not working, you're not making products and you have reactants just sitting there. Okay? So they asked you to calculate K. Well, all right. I have a new equation that has K in it. Okay? Delta G is minus RT natural log of K. All right. So, I just found delta G, didn't I? So plug it in for that delta G. So negative 250 kilojoules per mole equals, that's what I just found, was delta G from E. Now I take my delta G I found and plug it in. Now be careful, so minus has to stay. Now this on your equation sheet, this R constant, and it is this one because it has the energy unit in it and we're working with energy. These would be for gases right here. Atmosphere, that's pressure, torr, pressure. Okay, now I do see another issue. My delta G is in kilojoules per mole and my constant is in joules per mole. So I have to switch one or the other. I'm just going to switch my R constant. Again, to get from joules to kilojoules, you divide by 1,000. So 8.314 joules per mole Kelvin is the same thing as 0.008314 kilojoules per mole Kelvin. Okay, that's just a metric conversion. So there's my R. And temperature, was 25 Celsius in the problem, so that's 298 Kelvin. And natural log of K. We're trying to find K, right? So first thing I'm going to do is I'm going to move the negative sign over, multiply everything by -1. So, boom. And then divide by all this junk. How do you get rid of a natural log? E to the x button. So it's really e to the, oops. Alright. So I think this number comes out before you do the natural log part. I think that number comes out to be pretty close to 100. It's like 100 something. So 250 divided by 0.008314 divided by 298 Kelvin, 100.9 something something something. And that equals the natural log of K. So you have to do e to that number. E to the 100 point whatever. And you get a ginormous number. It's 6.6 times 10 to the 43rd. 6.6 times 10 to the 43rd. So, as we've already confirmed, the voltage is positive, so the reaction is happening. Delta G is negative, so the reaction is happening. It's releasing energy. That's what's giving us our positive voltage. K is ginormous. Reaction is favoring the products. When K is big, products are favored. right? Because K is products over reactants. So if K is large, products are large. What do we know about products being large? The reaction is happening. We've reiterated that the reaction is happening 3 different ways. With voltage, with delta G, and with our K value, equilibrium constant. Any questions? Okay. So there's the K value. Okay, so again to reiterate, if K is really, really big, the reaction favors the product, so the reaction's happening. That also produces a voltage because the reaction releases energy to give us a voltage. When K equals 1, the reaction is at equilibrium, which if it's at equilibrium, it will not produce a voltage. So no energy is leaving, but no energy is being added either. So reactions at equilibrium are not able to produce a voltage. Now, if K is smaller than 1, the reaction favors the reactants. If a reaction favors the reaction's like not working. So a negative voltage and energy would have to be put in positive delta G if you want the reaction to occur. So the forward way, the reaction is not working. Now you could make it work going backwards, but not forward. The forward reaction is not favored. So again, this is just like signs and conceptual. And again, these are under standard conditions, 25 Celsius, 1 atmosphere, 1 molar. So let's do a practice problem, MCQ, this is from a couple years ago. So it says, based on the information in the table, which of the following shows the cell potential and the Gibbs free energy for the reaction that occurs in a standard, so standard conditions, galvanic cell. Now the word this statement right here means the reaction is occurring. In galvanic and voltaic cells, they are based on spontaneous reactions, reactions that will occur. All right? So when you look at these reduction potentials, how do we know they're reduction potentials? Well, because the electrons are going in, the atoms or ions, are gaining electrons. So if this is a galvanic cell that works, we want to pick the one who's more likely to be reduced. Who is it? Chromium ion or magnesium ion? Who's going to get reduced? Chromium, because it has a higher reduction potential. I mean, it's not a great reduction potential, but it's better than magnesium's. So chromium is the thing that gets reduced. So we leave chromium as is. Which means this guy has to get oxidized. So if it's going to get oxidized, I'm going to flip its reduction potential backwards, so now that it's an oxidation potential. So I just rewrite the equation backwards. And when I flip it backwards, I also have to flip the sign. So when you take 2.37 and you add it to negative 0.74, you get 1.63. So C and D are out because the voltages are wrong. Boom. So now we need to calculate delta G. Well, delta G is minus NFE. Why do we use this one? Because we know E. We know the voltage. It's 1.63. All the others we can plug in. F is a constant, and N is moles of electrons. Now, moles of electrons, again, N, comes from these guys. And it's not 3, it's not 2, it's not 5. It's what you would do to match them, which would be a what? 6, right? You'd multiply this equation by 3, and you multiply this equation by 2, and that would be your balanced redox reaction, with N being 6 moles of electrons. So keep the minus in there. This is 6 again. Faraday's constant. Now remember, this is its constant in joules per volt mole. So I'm going to change it to kilojoules because if you notice, the table has kilojoules in it. and the voltage was 1.63. Now, so again, this is just the joule to kilojoule conversion. Technically, you would not have a calculator on this part. So here's what I would do, personally. I would not call this 96, because it sucks. I'd call it 100. It's pretty darn close to 100, right? So I'd be like, okay, this is like 100-ish, right? 100 times 6 is 600-ish. That's easy. 600 times 1 point something is going to give me 944 or 157. 600 times 1.6 something. Are you going to get 100 something? You have 600. How would you get 100 something? Right? So it's B. 600 times 1 point something is going to give you 900 something. That's the way I would have, I mean, you obviously have a calculator right now, but if I didn't have a calculator, that's the way I would have done it with estimating. I'd call 96 100 instead, because 100 is just an easier number to work with. Then 100 times 6 is 600, times 1.6 is going to, you only have two options, right? It's definitely not 100 something. So the answer is B. Okay. More practice. So the following two questions are based on this lead-gold redox reaction. So before we do anything, let's figure out who's doing what. Gold is being reduced and lead is being oxidized. Okay. So this is my reduction half reaction, and this is my oxidation half reaction. And basically, when you combine these, you should get 1.63, right? So this is what? 0.13, because 1.5 plus 0.13 is 1.63. But this is 0.13 when it's being oxidized. And they didn't ask for its oxidation. They asked for its what? Reduction potential. So what is it? Negative 0.13. Because the lead isn't actually doing this. The lead is doing the reverse of this. So if its oxidation potential is 0.13, its reduction potential is the opposite of that. Okay. Well, if the voltage is positive, what do we know about delta G? If this is a positive number, this whole term comes out to be negative, right? Releases energy. What else? If the voltage is positive, is a reaction happening? Yes. So the reaction favors the who? Products. If a reaction is favoring the products, K is big. K is big. Delta G, free energy, energy is being released. Negative. Question? All right. So it says the student wants to determine hydrogen peroxide concentration in a solution of hydrogen peroxide. So it's hydrogen peroxide and water. That's what the solution means. And the student is picking between two different titrants, dichromate or cobalt. Okay? And remember, so this is a redox titration. This is not an acid-base titration. Still, the whole point of this titration is to find an unknown concentration, just like it was in an acid-base titration. You're trying to find an unknown concentration. This just isn't neutralization. This is oxidation reduction. So you have these half reactions right here, and they ask you to use the information to calculate the dichromate one, as well as the second part is to do the cobalt one. So we're going to look at these entities separately. Okay? So let's look at the dichromate one. Now let's review on how we assign oxidation states, because it's needed. Oxygen's -2 most of the time. That gives me a total of -14 because there's 7 of them. Now my overall charge is -2. So this guy is +6. Why? Because 6 times 2 is +12. +12 and -14 give me a -2 charge. So chromium is going from +6 to +3. That's reduction. Okay, something that we haven't worked with all that much are peroxides. In peroxides, oxygen is -1. It's not -2. Now, oxygen is almost always -2, unless it's diatomic oxygen, O2, and then it's 0. But in peroxides, oxygen is -2. Here's why. Peroxide looks like this. O2, 2-. The entire thing has a -2 charge. So if there are 2 of them, each one of them has to be -1, because -1 plus -1, 2 oxygens, adds up to -2. So in peroxides, the oxidation state of oxygen is not -2. It's -1. So it's -1 here, and then it's going to 0 here. So it's being oxidized over here. So when I go to combine, I keep my chromium reduction half reaction, right? Or I'm sorry, dichromate. So I keep this guy because it is being reduced in that reaction. And I flip my hydrogen peroxide half reaction. Now you need to be careful. There are 2 reactions that incorporate hydrogen peroxide, but they're not equal. They're not on the same side of the reaction arrow. So which one of these, if I flip it, has hydrogen peroxide being oxidized? Because that's what's happening in that first reaction. The first one or the second one? Which one do I need to be flipping? It's the second one. If you flip the first one, here's what it looks like. This is water being oxidized. So that's not going to work. This isn't water being oxidized up here. It's hydrogen peroxide being oxidized. So that one doesn't work. Look when you flip the other, the bottom one. Hydrogen peroxide losing electrons. This is hydrogen peroxide losing electrons. So this is the voltage I use. Now I need to flip it, right? Because I have to flip the equation. So it's plus -0.70. I think it's 0.63. So this voltage is 0.63 volts. Okay, now we need to do it again, but for the cobalt and the hydrogen peroxide. So we need to kind of see what's going on with oxidation states in this second equation. So cobalt is +2, and it's going to +3. Ooh, that's an oxidation half reaction. Now we said in peroxides, oxygen is -2, right? And it's going, oh, I'm sorry, -1. And it's going to -2. So that's my reduction half reaction. So which one of these has hydrogen peroxide being reduced? Is it this one or is it this one? 1 or 2? Hydrogen peroxide gaining electrons. It's the first one. Who's being reduced in the second one? Oxygen. So I don't care about this one now. This is the one I'm going to keep. Hydrogen peroxide being reduced. 1.77. But the cobalt is in this reaction right here, being oxidized. It's going from +2 up to +3. So that means I have to, this is a reduction half reaction, right? So I have to flip it. So that's going to give me negative 1.84. Uh-oh. Yikes. That's a negative voltage. What does that mean? It means no reaction, right? This reaction won't happen. So it's probably not the thing you want to pick as your titrant. Because you'll just like pour it in there and 0 things will occur. So that's what they ask in the subsequent parts. It says, based on your calculated value of E, the student has to pick who they're going to use. So who should they pick? Well, they should pick the dichromate. Because the voltage is positive, and so the reaction will occur. And you could even go on to say that for the cobalt, the reaction won't occur. So what's the point of using it in a titration? Have fun doing your titration for the rest of your life that doesn't do anything. So then again, they ask you to calculate free energy. Now before we even do that, what's the sign going to be? Delta G will be what sign if the reaction occurs? So I know there's so many signs that can get so confusing. The fact that it releases energy for us to use, so negative delta G is good. A reaction will occur. I guess I shouldn't use the word good. I guess reactions not occurring could be good. But if you want a reaction to happen, you want the energy to be released so we can use it to do work for us. You want it to give us energy. We don't want to have to add energy. If we have to put in energy, we have to use resources to force it to work. Okay? So delta G is minus NFE. So delta G is, oops, I'm going to do this. I think I have a better slide, a blank slide. Okay. Sorry. I just want more space. Now, what is the moles in this one? So let's go back. Now, the nice thing is the half reactions are written for us. Now, we are doing whoa. Okay, brain not working. Oh my goodness. Okay, we're doing these 2 half reactions, right? We said this was the reaction we were going to do because it gave us the positive voltage, right? What will my electrons be? 8, 2, 6, 12. N moles of electrons is going to be what? How would you make those half reactions match? I know you'd have to flip one, but regardless of that, how do you make the electrons match? You would just do the bottom one, right? You'd multiply the bottom one by 3, and the moles of electrons would be what? This is a 6, and this is a 2. So 6. Okay? So N is 6. Faraday's constant is 96,485 joule per mole. Now, I know that I want this to be in kilojoules, so I'm going to cheat instantly and rewrite the constant in kilojoules. I did that by dividing by 1,000. And then the voltage was 0.63 volts, right, from that reaction? Let's look at volts. Ooh, you can't see that very well. Volts cancel. We're left with kilojoules per mole. Don't forget about the negative. So calculate it out. I don't know what it is. 2 sig figs again. 360. So what does this mean? This much energy is released. And then we isolate it, and it does work for us, like turn on a light bulb. Questions? Okay, I'm skipping these for now because we have to get to other stuff. So here we go. These are standard conditions. It used to be, back in the day, on the equation sheet, they gave you this equation. It's called the Nernst equation, okay? And they gave you this equation, and they expected you to do math with it. Now, I will do math with it one time, but you are not expected to do math with it. You're expected to do this qualitatively, not quantitatively. So here's the deal. What they did is they said, okay, the voltage will be different than we predict if we mess with one of the conditions. So if we're not at standard conditions, the voltage will be different than what our predicted voltage will be. Sometimes it will be higher and sometimes it will be lower. And it's going to be your job to be able to understand this qualitatively. Okay? So this means non-standard. What's the difference? There's no circle with it. Okay? So this means the standard voltage, and then you have this whole term. Okay? And then what they did is they took R and T and F and they rearranged it with logs and stuff. This is what R, T, and F combined are. This is moles of electrons still, and this is log of Q, where Q is products over reactants. And it's Q because you don't know if you're at equilibrium or not. All right? So when the voltage of a cell is 0, you are at equilibrium. Okay? So we're going to do this quantitative and qualitatively, and then just know that you don't have to do any math, but I'm going to show you the math to prove my point. So here's how this works. I'm not going to use this. Okay? We're going to look at a copper zinc cell. Okay? We know that the copper zinc cell, this written this way, is spontaneous, meaning it will happen, it will produce a voltage. Okay? Now, when we calculate its voltage based on reduction potentials, we are assuming that the concentration of this guy is 1 molar and the concentration of this guy is 1 molar, because that's what it means to be under standard conditions. Notice I don't care about the solids because solids are irrelevant when we're talking about concentrations. Okay? So when Q equals 1, okay, let's see. When Q equals 1, because, right, Q would be 1 molar over 1 molar. It'd be products over reactants raised to their respective coefficients. Well, the log of 1 is 0, so this whole term goes away. So if Q is 1, the non-standard voltage is what we would expect it to be for the standard voltage. It wouldn't be any different. However, if we start, for example, messing with concentration or pressure if they're gases and they're no longer 1 molar, this can drive a reaction forward or backward depending on who is more concentrated. So what happens when Q is less than 1? Well, let's talk about what that means. Q is less than 1. Okay, that means favor or too much reactants, right? That's what gives you a small q. So more concentration of reactants. So I'm going to make up an example, a fake example. I'm going to say, okay, my reactants have more concentration. So I'm going to call this 3 molar, and I'm going to call, or I want to call this 5 molar. And I'm going to call this 1 molar. Think of this in terms of Le Chatelier. If you have too much concentration on the reactant side, which way do you shift? To the products, right? Now, in these electrochemical cells, the more product, the more that you can drive the reaction to make products, the better of a voltage you can get. So if you have too much reactants and it's causing the reaction to drive through the cell towards the products, your voltage is going to jump up a little bit. It'll be slightly more than what we would have predicted using our reduction potentials. A little bit greater, okay? So what happens if Q is too big? Well, what does that mean? So if Q is big, it means we have high concentration of products. So I'm just going to flip those numbers. I'm going to call this guy, the zinc, 5 molar, and the copper ion 1 molar instead. Uh-oh. What happens if your products are too concentrated? The reaction is going to want to go backwards. That is not good for a cell whose reaction wants to go forward, right? Because you need the electrons to move one direction, anode to cathode. So if your reaction is driving backwards, your voltage is going to drop a little bit. It's not going to be as good of a voltage because of the concentration gradient difference. Too much product will drive the reaction backwards. Driving a reaction backwards will drop the value a little bit. The voltage will be slower slightly because you're going the wrong direction. You want to be going forward, not backward. Okay? God. Okay. So this is qualitatively. If you can explain the difference in voltage just qualitatively without numbers, that's totally all you need for the AP test, okay? So again, if you mess with standard conditions, it will change the voltage of the cell. It will be different than we normally would have predicted from our reduction potentials, okay? So I'm going to give you an example. Or actually, we're going to do this one, and then I'm going to do math one time, and then we won't ever do the math again because you are not required to do the math. So look at same exact cell, the zinc copper cell. It's a pretty popular cell to work with for electrochemistry. So they tell you the zinc ion is 5 molar, which is not standard, right? Standard is 1 molar. And the copper ion is 0.3 molar, which is also not standard because standard is 1 molar. So too much concentration of product will cause the reaction to want to go backwards, right? So what's going to happen to the voltage compared to its normal voltage or its standard voltage? If we're working backwards, the voltage is going to drop a little bit. So the voltage would be slightly lower than predicted. So I'm going to use math to prove that. I'm going to use the Nernst equation, okay? We're at 298 Kelvin, which is 25 Celsius. So E, voltage under non-standard condition, is whatever the standard voltage would have been minus this number. Again, I'm doing this with you. Okay, so let's figure out what the standard voltage would have been. Well, we need reduction potential tables for that, right? So the copper is being reduced, so we'll use copper's reduction potential, and the zinc is being oxidized. So copper being reduced is here, 0.34, so we'll keep that guy. And the zinc being oxidized would be this guy flipped backwards, because this is zinc being reduced, so positive 0.76. So 0.34 plus 0.76 gives us 1.10 when you add them together. So that's standard potential. But we aren't under standard conditions. How do I know? Because I messed with the concentrations. They're not 1 molar. Standard conditions are 1 molar, and they're not 1 molar right now. So I put the 1.10 in there, right here. Oop. Now, the moles of electrons are actually easy on this one. This is +2, and this is losing 2, this is gaining 2, so it's 2. They're both the same, so it's 2 moles of electrons for the N. That's what goes down here. It's moles of electrons. Log of Q. Well, Q is products over reactants. My product is 5 molar. My reactant is 0.3 molar, right? So I would just calculate this whole number out and then subtract it from 1.1. So log of 5 divided by 0.3 times 0.0592 divided by 2. So it's non-standard, is 1.10, which is standard, minus this whole term comes out to be 0.036 something something something. So what happened to the voltage? It dropped. Now, it didn't drop a huge amount, but it still dropped. So now instead of the voltage being 1.1, it is 1.06, which is what we predicted qualitatively. I just wanted to prove it to you quantitatively. Okay? They didn't just like pull it out of nowhere, right? So mathematically, that does show a drop in voltage because we have too high of a concentration of reactants. Or I'm sorry, of products. And so the reaction will want to go backwards. And going backwards does not help us with voltage. We want to be going forward, reactants to products. Okay? Okay. So the next part is concentration cells. So these are electrolytics, or not electrolytic, these are cells that work and produce a current just based on concentration difference. So it's not like the copper-zinc one is involving 2 different species, copper in one and zinc in the other. This is being driven by the same species with a concentration gradient, meaning one side is more concentrated than the other. Specifically, it's the cathode that's more concentrated than the anode, okay? And so what happens, and I will show you with this example, you have at the anode, oxidation is occurring, nickel going to nickel 2+, I'm going to put D for diluted. And then at the cathode, those 2 electrons that the nickel is losing are being taken in to turn the nickel back to solid where C is concentrated. So think about it this way. When you go to write out the overall reaction, solid nickels cancel, 2 electrons cancel. You have nickel 2+ concentrated going to nickel 2+ diluted. So look at high concentration on the reactant side will drive the forward reaction. If you drive the forward reaction, you'll be able to produce a voltage. Okay? So this is only powered by a concentration difference, not an oxidation reduction difference based on cell potentials. These guys have the same cell potential, one way or the other. That's the same number and it's flipped. So if you combine them, you get 0. What we've done is we've forced our reactant to be higher concentration. Maybe this guy is 10 molar while this guy is only 3 molar. If you can get the forward reaction to occur, you will be able to produce a voltage. So this is a reaction occurring based on concentration difference as opposed to reduction and oxidation differences. Okay? So that's what a concentration cell is. All right? I'm not going to make you calculate this. So the last 2 parts I have for you today, electrolysis. So this is the exact opposite of everything we've been doing. These are chemical reactions, redox reactions, that don't work. So well, you know what we do? We force them to work by supplying energy. These are delta G positive, E negative. And how do we get them to work? We put in energy. We supply electricity to force the reaction to happen. Okay? Again, anode has oxidation, cathode has reduction, just like our voltaic cells. And I'll give 2 examples. So, for example, first one, you have sodium chloride, right? Molten sodium chloride. This means liquid. meaning it's pure sodium chloride. There's nothing in there like water or anything else. So it's Na plus and it's Cl minus. Okay? Now, when you start doing these types of problems, this electrolysis, you have to understand that when sodium has lost one electron to become plus one, it is as oxidized as it gets. Like, it's already lost one. It's not going to lose anymore. Meaning, if you have to choose who's going to be oxidized in this guy, it's not going to be sodium. You already maxed out sodium's oxidation. It's already oxidized. So if something's going to happen to it, like if you're going to force something to happen to it, it can't be oxidation. This guy can be reduced, though, right? It could take in electrons and drop down. And then the same thing is true for chloride. Well, in a different way, though. Chloride has gained one electron. That's reduction, right? It is as reduced as it gets in its minus form. So this guy can't get reduced anymore. It's as reduced as it gets. So if something's going to happen to it, it's going to be oxidation. So you notice at the cathode where reduction is happening, I have the sodium ion being reduced to solid sodium. Whereas at the anode where oxidation occurs, I have the chloride ion being reduced into Cl2. Well, Cl2 is a gas. So around this electrode, you'd see bubbles. Okay? So literally bubbles would form around this electrode during the reduction, during the oxidation of chloride ions to chlorine gas. Okay? And again, this only happens by putting in energy. This is not a spontaneous reaction. This is like we're supplying a current to force this to happen. All right? So here's the tricky part. Again, I'm probably not going to finish during class, so I'll finish up on my video. Here's the tricky part. When you start doing electrolysis in aqueous solutions, not only do you have the salt present, but you also have water. And the issue becomes is that water has the potential to be reduced and oxidized as well. So now there's a fight for who gets reduced and who gets oxidized when water is present along with the salt. Okay? Now, when you go to your reduction potentials, can be confusing. I want to make it clear that there's two water equations, and they aren't the same thing. This right here is oxygen being reduced, which means if I flip it backwards, it is water being oxidized. But it's not water being reduced the other way, so you have to be careful. Water being reduced is down here. Here's water taking in electrons to be reduced. And then notice that if you flip this backwards, it's not water being oxidized, it's hydrogen gas being oxidized. So there are two separate water equations you have to pay attention to. Okay, so here we go. Calcium iodide. Now, before we even look down here, who will be reduced between calcium and who will be between calcium and iodide, and who will be oxidized between them? So calcium has lost 2 electrons. It is not going to lose any more electrons. So calcium has the potential to be the reduced species, but not oxidized. Now, iodine has gained electrons. It doesn't want to gain anymore. So it won't be the thing that gets reduced. It will be the thing that gets oxidized. Now the problem becomes, for our reductions, calcium has to fight with water because this is an aqueous solution, and there's water in there. That's what it means to be aqueous. So here's calcium being reduced, and here's its reduction potential. And then here's the reduction of water. Uh-oh. Who wins? Who's going to get reduced, the calcium or the water? The water. So the water would actually be the thing that gets reduced. And so what does the calcium do? Nothing. It literally just sits there and does nothing. So this is the reaction that will happen at the cathode. Okay? Now, I don't like this, so I'm going to rewrite this. Because this is how it will be present on your test. And I'll write the water one over here. Please bear with me right when the bell rings. Okay. These are reduction potentials. Okay. So I just flipped them backwards and I gave you reduction potentials. Those are reduction numbers. Okay. And now we know, though, that the iodide is not going to be reduced. It's going to be oxidized, right? So that means I will flip it. And when I do flip it, this guy, I will get this guy right here, right? Okay. So that's its oxidation potential. I don't like that it wrote reduction because that isn't its reduction potential. Okay. And then when I flip this one backwards, I flip this sign, right? Okay. And now I have this guy. So then the question becomes, well, who's going to get oxidized? Well, whoever has the better oxidation potential, which is the iodide. So the iodide will be at the anode, and the water will just sit and float around. So when you look at this real quick, I know the bell's going to ring, just bear with me. Here's a picture of it. You notice that iodide is being oxidized to solid iodine. Now iodine's a solid, so this electrode right here will gain mass because the solid will stick to the electrode. Okay? Whereas at the cathode, the water was the thing that got reduced, producing hydrogen gas, which is why you see bubbles, and hydroxide. And I need to point something out. If you were to put phenolphthalein in here, it would turn pink over here because phenolphthalein is pink in a base and you are producing hydroxide ions, which are basic. So understanding that this area could turn pink because of the presence of hydroxide ions during this electrolysis is really important. Okay, you're making hydroxide, which is basic. Okay. All right, so electrical current is the amount of charge, which is measured in coulombs, that passes through the cross-sectional area, so usually like a wire. That's the medium that we're using per second. So charge over time. So for on your equation sheet, you have the equation that's I equals Q over T, where I is current, also known as amps, and an amp is a coulomb, which is a unit of charge, per time. Coulomb per second. So an amp is a coulomb per second. So sometimes it is helpful to rewrite the unit amp as coulomb per second when we're gonna end up doing dimensional analysis. Okay, and then if you know coulombs, you can actually start converting to moles of electrons using Faraday's constant. Oop, that's missing an A. Sorry. So Faraday's constant is that this many coulombs of charge for every 1 mole of electrons. So if you know charge, you can start converting charge to moles of electrons, and then we can actually take that out further, which I'll show you when we practice. So first, it says how much charge. All right, well, charge is coulombs. Okay, so that's what they're asking for. Passes through a cross-section of a wire that is carrying 0.987 amps. And the time is in minutes. Now remember, so I equals Q over T. Well, they give you amps, that's I, okay? And then they give you time. The problem is time is in minutes. So you have two options. You can convert minutes to seconds right away, or you can do it as part of the process. So if you're asking for charge, that's letter Q. So I times T is Q. So I is 0.987. Oops, let me do this down here. I is 0.987. Now I'm going to rewrite the word amp as a coulomb per second so you can see how the units work out. Okay, so there's I times time. Well, the time isn't given in seconds, so we're going to have to convert it. So look at 12.3 minutes, right? The minutes and the seconds won't cancel. So what do we say? We say 1 minute, 60 seconds. That gets the minutes to cancel and the seconds to cancel, and we're left with coulombs, which is charge, Q. So you calculate it out and you get 728 coulombs. Okay. So then to take this further is if you know charge, this is charge in coulombs. Coulombs is our new unit for charge. they want to know how many moles of electrons. Well, moles of electrons are related to Faraday's constant, okay? So 728 coulombs of charge, and then you use Faraday's constant. Faraday's constant is 96485 coulombs for every 1 mole of electrons. So the coulombs go on the bottom, right, because we're trying to get rid of it. Oops, 85 coulombs for every 1 mole of electrons, which is 6.02 times 10 to the 23rd electrons. And you take and you divide this, and this is how many moles of electrons we're working with. So again, this is just basic algebraic arrangement. So we used I equals Q over T. We rearranged this all for Q, and then we used Faraday's constant to get us from coulombs to moles of electrons. And this is going to actually eventually take us further as well. So something that is this is often used for, is for electroplating. So, right, you take a piece of metal and you want to put silver on it, and you plate the silver on it by applying a current. So you put it in like a solution of like silver nitrate, right? And then you supply the current, and the current forces the silver to be reduced onto its, the thing is acting like an electrode, okay? And you can plate it with silver or other things as well. So it's called electroplating, and that's done by supplying electricity, electrolysis, or an electrical current. You supply a current to force the silver, in my example, to be reduced. So look in this one, is they're asking you to make aluminum. So basically you're electroplating aluminum, okay? And what they do is they probably take a piece of aluminum, they stick it in a solution of aluminum, like maybe aluminum nitrate or aluminum chloride, and then they supply a voltage, and they get that aluminum ion, right? Because that's what this is. This is Al3 plus in aluminum chloride, okay? And they're turning it into solid aluminum. It's called electroplating, okay? So you have ions turning into metal, solid metal, okay? And that metal sticks to the surface of another sort of metal, whatever metal you're using. So, right, you can like change pennies, right? You could take a copper penny and, put supply a current to it and coat it or plate it with a different metal, okay? And it'll look like it's not copper anymore. It'll be coated with whatever metal it is. So this involves dimensional analysis. So notice they give us current, which is I, and they give us time, which is T. So if we look back at our equation, I equals Q over T. If we know I and we know T, we can find charge. Now we have to be careful because, again, time is measured in seconds, and the time they gave us was in hours. I think it was an hour. So the current supplied in the problem was 10 amps. So I'm going to rewrite that as 10 coulombs per second. That's the current. That's this guy. Equals Q over time is 1 hour. Okay? So right, multiply both sides by 1 hour. So now you have 10 coulombs per second times 1 hour. This is not going to work. Your units of time need to be in the same unit. So we need to do a little bit extra work. Now you could do it in the front end where you convert hours to seconds in the beginning. I'm just doing it right here. So 1 hour is 60 minutes, and 1 minute is 60 seconds. So look at the hours get converted to the seconds, and now we have the seconds cancel out to give us charge. Okay? So this will give us our charge. So 10 times 60 times 60 is 36,000 coulombs of charge. Okay? Now in this problem, they don't ask you to stop here. They ask you to get the grams of aluminum solid. How much, if they supply this current in this, under these conditions, how much for an hour, how much solid aluminum could you get to plate out, to do electroplating? So the first thing you want to do once you have coulombs is what we just did in the last problem. Let's change coulombs using Faraday's constant to moles of electrons. And the reason that we're going this direction is because during electroplating, you are taking aluminum ion from the aluminum chloride and you're reducing it to solid aluminum. it is a redox. Well, it's a reduction process by supplying a current. So that's why these moles of electrons are helpful, because look what this is. There are 3 moles of electrons being used, this one, for every mole of aluminum that's being plated. For every one, oops, I wrote silver, I'm sorry. My bad. Okay. And now that you know moles of aluminum, you can turn it to grams our good old-fashioned way. Okay, so this is the reduction process. So Faraday's constant is what helps get us to our moles and then officially grams, because the moles of electrons are the amount of electrons used during the reduction of aluminum ion to solid metal aluminum. Okay, and so if you do this, you take 36,000, you divide it by 96,485, you divide it again by 3, and then you multiply by 26.98, and you end up with 3.36 grams of aluminum. So you could plate out 3.36 grams of aluminum during this process if you ran this system for an hour. You supplied this current for 1 hour, okay? Which is pretty cool, right? We just took aluminum in solution and we plated it out by supplying energy, right? We had to put in energy to do this. Okay, but we supplied a voltage and it allowed us to turn the aluminum ion in solution to solid aluminum. So that's pretty neat. It's called electroplating. Okay, so 3.36 grams. And then again, this down here is just like the flow chart, right? Current and time gives you coulombs. So current and time gives you coulombs, which is charge. Then you can use Faraday's constant. So that gives us charge. And then you use Faraday's constant to go from charge to moles of electrons. And then you use the redox half reaction to go from moles of electrons to moles. And then you just convert into grams the old-fashioned way. Okay, so again, this is just a flow chart. So like you technically could start here and go backwards as well. It doesn't matter which way you go. You can start anywhere in the flow chart. You just have to flow the correct direction. Okay? So we're going to do another practice one. It says, how long would it take? Oh, so this one is asking time. So we're trying to get T, and they want it in minutes. So just know that we'll probably get it in seconds and then have to convert it to minutes at the end. So we want to plate out. We want to get solid silver from a solution containing silver ions, and we know current. Okay, well, I equals Q over T, right? And we want to know time. We do know current, it's given, but we don't know charge. So basically, we want to use this info to get us Q, because once we know Q and we know I, we can solve for T. So let's figure out how to go about this. So let's look at what's happening. They're taking silver ion and they're turning it into solid silver. What does that require? It requires adding 1 electron. Silver ion takes in 1 electron from the current, right, to make solid silver. So we're going to work backwards. Watch. 3.5, oops, do a different color. 3.56 grams of silver. And then silver is 107.87 grams per 1 mole of silver. So we're right here. Now we're going to work backwards to go to moles of electrons. 1 mole of silver will take in 1 mole of silver requires 1 mole of electrons. 1 mole of electrons is using Faraday's constant, 96,485 coulombs. So look, that is charge. So this will get us Q, which is coulombs or charge. So we calculate this out. 3.56 divided by 107.87. 1 and 1 right here aren't going to do anything. So grams cancel, moles cancel, we're left with charge, coulombs. And we have to multiply by 96485, Faraday's constant. This gives me, I'm going to keep the whole number. So Q ends up being 3184 point whatever. Keep the whole number in your calculator. Coulombs. Okay? Well, I equals Q over T. So we need to solve for T, right? That's what it's asking for, is time. So I'm rearranging to solve for T. So I get T off of the bottom. And now I'm going to divide both sides by I. So Q over I is T. That's the equation. That's the algebraic manipulation. Why is it doing that? Don't do that. Sorry. T equals Q over I. So I'm going to go ahead and, let's see where I can do this. T equals, so my charge was 3184 something 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 coulombs divided by I is current, and current is this. Now remember, an amp is the same thing as a coulomb per second. So I'm going to rewrite this just so you can see how the units work out. 2.5 coulombs per second. So you can see that those coulombs cancel and we're left with seconds. Now this would be fine, except for I didn't ask for seconds. I asked for minutes. So we'll solve for this in seconds. And we get 1273.7 something seconds. And what do they want it? They want it in minutes. So this is just normal dimensional analysis. 60 seconds in 1 minute. So we convert our seconds to our minutes. So divide by 60. And you end up, if it's, so this is 2 sig figs right here. This is 3. So your answer is 2 sig figs. So 21 minutes. So to plate out this many grams of silver with this amount of current, it'll take 21 minutes to get that much solid silver out of this electroplating process. So this is kind of just like a picture. So look, they take like this silver electrode, right? And then you have like silver solution in here, whoever it is, silver nitrate, let's say, all right? Okay, and you supply a current, which is allowing the electrons to come in here, and they're hitting up the silver ion, and then it turns into solid silver. So the whole spoon gets coated with solid silver. So again, it's called electroplating, where you plate metals on the surfaces of other materials, usually other metals. Okay, and again, this is done by adding energy, specifically electricity. Okay, so they supply an amp of, a current. Okay. So again, this is the like the dimensional analysis part of electroplating.